Morning everyone. Today our topic for the subject of digital signal processing is analysis of linear time invariant system, in short or abbreviated form, that is called LTI system. Linear time invariant system. The system should be linear system as well as the system should be time linear system, time invariant system also. So when a system is defined by a linear system as well as time invariant system, those type of system is known as LTI system. And today we will learn about how the system, the LTI system in overall system is being analyzed with respect to different type of transformations. So initially, whenever we want to discuss about the analysis of LTI system or linear time invariant system, let us try to acquire some knowledge or definition or gather some idea about what is LTI system. LTI system, the name itself defines it's a linear time invariant system. That means some linearity portions are there for that of the system properties as well as some time invariance properties also there for that of the system properties. That means a system having the property of linearity as well as time invariance is known as an LTI system. What is linear property? The linearity of a system is defined by a system that possesses the property of superposition. When a system follows the property of superposition, that is known as a linear system. A system having linear system have to be defined by a LTI system. That means whenever system is defined by LTI system, the system has to follow the position of superposition theorem. Has to follow the theorem of superposition theorem. That means it abide by the rules of that of the superposition theorem or property. That is the first criteria for LTI system to be a LTI system. What is the second criteria? The second criteria for LTI system is that time invariance. A system is time invariant system. What is time invariant system? Basically, whenever a system is defined by a time invariant system, that means the input-output behavior for that particular system will never follow the change of time, will never changes with respect to that of the change of time. With respect to the change of time, the system output can change. With respect to the change of time, the system's input can change. But overall, the behavior or the characteristics between input-output relationship does not follow the variation of time. A system is time invariant in such a way that the behavior or characteristics of that particular system are fixed over time. The behavior characteristics means the input-output relationship. A system follows this rule is known as a time invariant system. So what we have to follow that means whenever we want to analyze a LTI system, at first the system should be a LTI system. So LTI means the system should has follow the property of linearity as well. The system should be a time invariant system. If a system having followed this one, then that system is a LTI system. Now we can follow the position or properties of that particular system. Now, how the linear time system can also be defined by a discrete time system, can also be defined as a continuous time system, depending upon the nature of that of the system, depending upon the nature or behavior of that of the feeding input of that of the system. If the input feeding to that of the system is continuous time system, that means it can be defined by x of t, that will be defined by a continuous time LTI system. But if the system follows only discrete time inputs, whenever the input is feeding or that of the system, it will always a discrete time system. Then those type of systems are known as discrete LTI system. So in that way, depending upon the feeding input of that particular system, LTI system can also be defined by two ways: continuous time LTI system and discrete time LTI system. So let us start with the simple sequence. As we are dealing with the DSP, that is digital signal processing, certainly we have to follow the rules for discrete sequences firstly, preferences for discrete sequence first. That's why we are starting with the discrete time LTI system. What is discrete time LTI system basically? So whenever we are doing the analysis for LTI system, we have to follow that whenever system is defined by input feeding to that of the system and the system is being characterized by the system impulse function, certainly there will be some convolution is there. That means some manipulations are there between the input feeding to that of the system and the system characterization, so that by manipulation of those two forms of signal, we are gathering the output, we are getting the response for that particular system. So that gathering, that manipulation, whatever is being done within that system, that is LTI system, is known as convolution. But whenever it is a discrete time system, discrete time signal, that is known as convolution sum, because summation is there for the calculation of that of the output. Now what we can do, the representation of that discrete time signal in time impulses, in the term of impulses, whenever it is being defined by impulse function, that means nothing is fed to that of the input, the only input function is there, that means it will be a convolution sum with that of the impulse train of impulse function. Certainly it can be represented as x of n is nothing but summation of k ranges from minus infinite to plus infinite, x of k multiplied by del of n minus k. That means whenever a system is being multiplied by impulse train for different values of k for negative and positive values, and if we sum all the values of there, we are certainly getting the value of that input for that discrete LTI system. What we have to define here, it is being defined that the value of delta n minus k represents unit impulse function at the value of n equals to k, as simple as that. Clear? Now how that convolution sum is being represented by using block diagrams. So whenever two systems are there, whenever we are doing the convolution sum, in our last summation, x of k is being multiplied by del of n minus k. Now what is del of n minus k? Del of n minus k, whenever it is being transformed by that of the system, it is in that block, it is written that system t. T means whatever the transformation is being done by that of the system is being defined by hkn. So whatever the functions are there in terms of impulse train, the delayed impulse function del of n minus k, that is being transformed by that of the system, so that at the output we are gathering some function that is defined by h of kn. Similarly, whenever the input function is there, x of n, that is the input feeding to that of the system, it is also being transformed by that of the system, and we are gathering the output as y of n. So y of n is nothing but the output for that LTI system, that is discrete time LTI system. So that can also be defined as the response for that of the system. So by analysis of that LTI system, we are simply calculating the response of different kind of systems. So response y of n now can be calculated as simply defined by the transformation of x of n. And what is x of n? In our last class, it is defined that in our last slide, it is defined that x of k is nothing but is equals to summation of this one. So if I do this one in that way, we are simply putting the value of x in there within that summation and that the value of transformation t. So what it actually defined, that is summation k ranges from minus infinite to plus infinite, x of k is there, then there will be delta of n minus k. Now transformation is being done on that of the system, so it will be defined by t of del of n minus k. So whenever we are doing the transformation of del of n minus k in our first block, what are the transformation output? That is nothing but h of kn. So in that system, it will be defined by x of k multiplied by h of kn. Whenever these two terms, the first term is feeding input, the second term is system function, whenever they are multiplying with each other and they are summed up for different values of k negative to positive, we are simply gathering the output of that particular system. We are simply gathering the response of that particular system, and that system is nothing but a discrete time LTI system. So in that way, the responses or analysis of LTI system can be defined as simple by using convolution sum logic. Why we are using convolution sum logic? Convolution means we are simply convoluting the system function as well as the input function, and sum means the summation is being done. As it's a discrete time system, so there should be summation. In that way, we can easily calculate the system response or system output for that particular system. So next one, as the system is being defined by a time invariant system, LTI, the term Ti means time invariant. As the system is also defined by a time embedded system, therefore we can say the responses to time shifted unit pulses, therefore we can say the responses to time shifted unit impulses are also time shifted version of each other. As simple as that. It is very clear. That means we can say if we do the value of h of kn, that is nothing but defined also as h naught n minus k, as the response to times in shifted unit impulses are also time shifted version of each other. And thus Unit impulse function can also be written as simply as hn for the input impulse function of del of n. That's how we are written in that our last slide, that in function of a del of n minus k, whenever we are applying the transformation for that particular system, it is being represented as h of k n. So in that way also it can be defined as the unit impulse function response. Unit impulse response can be written as simply h of n for the unit impulse function of del of n. As input is del of n, its output is h of n. So h of n is nothing but defined by the system impulse function. So in that way, del n and hn are correlated with each other. So therefore we can say, for an LTI system, if I want to discuss the analysis of a LTI system, that is simply we are putting the calculation for finding the value of extracting the value of that of the response for that particular system, that is LTI system. Simply the response y of n can easily be calculated by the convolution sum of x of n and h of n, and they can be simply written as by using that formula of y of n is equals to summation of k minus infinite to plus infinite x of k into h of n minus k. We are simply putting the definition for convolution. Whatever the function of convolution is there, if I want to find out the convolution of x of n and h of n, that is simply defined as summation of x of k into h of n minus k. We are simply following the same logic. So it is clearly mentioned in that convolution that whenever we want to find out the response for any kind of LTI system, certainly we have to make the convolution of input feeding to that LTI system and by the system impulse function. So system characterization of system impulse function is simply defined by h of n, and if it is being convoluted with that of the feeding input of that particular system, we are simply gathering the output or response for that particular LTI system. And in that way, by logical form of convolution, we can say that is the convolution or superposition sum, which can also be written as y of n is nothing but simply defined as x of n convolution with y of n. So in that way it can also be defined by, so yn is nothing but the responses for that LTI system, and it can easily be calculated by simply doing the convolution of x of n with y of n. Sorry, it will be h of n later, because whenever we are doing the convolution of x of n and y of h of n, we are simply gathering the value of y of n. Now, as we have already discussed about the discrete time LTI system, now it's come forward the next type of LTI system, that is continuous time LTI system. Whenever we are doing the continuous time LTI system, certainly we have to follow the integration rule, because it's a continuous time and continuous time does not follow the formula of summation. That summation will be converted here as integration. That's why the convolution sum here for continuous time system will be defined as the convolution integral. A similar approach can be drawn for continuous time LTM system also, and following the results can be easily be derived. In those cases, it will be defined by y of n is nothing but summation of x of k dot h of n minus k. But whenever we are doing it for continuous time system, it will be defined by y of n. In place of y of n, it will be y of t. Summation will be converted here as integration. The range will be same from minus infinite to plus infinite. X of k becomes x of capital T. H of n minus k becomes h of t minus capital T. And overall that integration will be within the value of t with respect to that of the value of capital T. So, or simply it can be defined as y of t is nothing but defined as convolution integral of x of k, x of t with h of t. So it can be simply defined by the equation of the last equation as y of t. The continuous time LTI system response can easily be calculated if I do the convolution of the system input as x of t with h of t. So in that way you can easily find out the responses for LTI system. So we have come across what are the different types of LTI system and how the system response can easily be calculated if the system is a discrete time system as well as if the system is a continuous time system. Now let us have some look about the properties of LTI system. There are several types of properties are also there. Basically, there are three type of properties are there for Lti system. Lti system properties are nothing but simply following the rules for the properties of convolution also. The convolution has three properties: commutative property, distributive property, associative property. Here also for Lti system also it has three properties. First one is commutative property, second one is associative property, and third one is distributive property. What is commutative property tells us? Commutative property tells us that whenever we are doing the convolution of xn with h of n gives the same result as we are doing the convolution of h of n with the value of x of n. If the input is x of n for a particular system and the system is being defined by h of n function, will give the same result as if the system's input is h of n, and it will be followed by that of the value of system characterization as x of n. That means whenever we are doing the convolution between a to b, that is gives the same result if the convolution is defined by b to a also. Second property is for that Lti system is associative property. What is associative property tells us? If we do the convolution of x of n with the convolution result of h1n and h2n, if there are two systems are there, one is defined by h of 1n and another system will be defined by h2n. Whenever we are doing the convolution of the system input x of n with the convolution result of h1n with h2n, that gives the same result, or it simply equals to that of the same value as the system input x of n first doing the convolution with the any first system as h1n, then its result whenever it is being convoluted with the another system function, that is h2n also. So in that way it will be associative nature with respect to that of the convolution. And third property is defined as distributive property. What is distributive property tells us? If we do a parallel circuit, parallel form of that of the system as defined by h1n and h2n, and whenever we are getting the result of that of the parallel form, certainly we are getting the value of h1n plus h2n. And if that parallel form of that particular system is being convoluted with that of the system input as x of n, certainly we are getting the output or response for that particular system as x of n convolution with h1 plus h2. Now it is a total form. Now that gives the same result or same response for that particular system whenever it is being defined by the convolution individually input with first system, individually input with that of the second system, and then sum them up. So finally distributive property can be tells us as that x whenever convolution with h1n plus h2n gives the same result or just equal to that of the value of x convolution with h1 plus x convolution with h2. That is tells us that the distributive property. So in that way these are the properties of Lti system. So next one, whenever we are getting the property of that of the system, we are gathering the idea how to find out the response or output of that particular system. The system should be stable in nature. So we have to define the stability for Lti system also. We have to consider about the stability for that Lti system also. An Lti system is stable. The logic is that a system is said to be a stable system if for each and every bounded input value of that particular system produces a bounded output. Then those type of Lti system can be defined as a stable system. For each and every bounded input, that means the value of x of n is also bounded. That means its value will be limited to bounded value, that is a finite value. Its value will be defined by less than of b for all values of n. Therefore, we can say whenever the input is bounded, if the system is stable, the output is also bounded. That means the value of y of n also finite or bounded. It can also be defined by the less than of an infinite value. Now, if I do the convolution of these two, x of n and h of n, and gathering the result as y of n, and for the condition of stability, if the value of input x of n and the value of output both are bounded, that means the value of x of n is under bounded value, finite value, the value of y of n is also finite value. So in that case we can say the system function, it can be defined as summation of k ranges from minus infinite to plus infinite. The value of h of k should also be bounded. as input and output for that particular system is bounded. So if the value of each of k, summation value within any value of k is under infinity, so that system can be defined as a stable system. The stability criteria for a particular LTI system can be lies by using this equation. The summation of k ranges from minus infinite to plus infinite. Mod of h of k should be less than infinity. So in that way, stability analysis of that system, LTI system, can also be done. So with respect to that of the stability of that of the LTI system, the causality of LTI system can also be defined. The causality and stability are the most two beautiful characteristics of LTI system. What is causal system? A system is said to be a causal if output at any time depends only on the values of input at present and past. It will be never dependent on that of the future values. That will be an unrealistic system. So causal system is that a system will be defined by a present and past values of input. That means we can say the system nature, system characterization or system impulse function h of n should be absent or equals to 0 for any values of future. That means the value of n less 0. For any value of n negative, it will be a future value, non-realistic value. So it should not follow that one. That's why the system will be defined as a causal system if its value will be 0 or absent whenever we are putting the values of n equals to negative. That defines the causality of that of the system. So in that way, the basic ideas of LTI system is being gathered. What is LTI system? How the responses of LTI system can be defined? What are the different types of LTI system? Now how it is being defined by convolution sum and convolution integral, depending upon the nature of that of the input of the system, whether it is continuous time system, whether it is a discrete time system, and how the system stability and the system causality can be defined also according to that the properties of LTI system can also be defined there. So that is our today's class. Thank you everyone.